Hello, this is the determination of shear center on open cross sections by Pierce Condo, Jacob Sparages, Rachel Shiflett, Joe Mesner, Brendan Quiones, and Kiara Cornell, section A3, and our TA is Comer. We're going to start off with the objective. The objective of this experiment was to design and show our abilities in measuring the shear center. So to do this, we had to design an experiment and a procedure where we had to consider boundary conditions, loading, and the geometry. First, we have to start with what the definition of the shear center was. For a shear center to be true, it has to have the sum of the moments have to be equal to zero. It does not physically have to be on the body, but it's something we had to keep in mind during this experiment.
For our theoretical calculation of shear flow, we have the following equations. First off, we have the moment of inertia, which is the base times the height cubed divided by 12. Keep in mind that for the orientation of an object, the base and the height variables may be switched depending on its x or y or even z orientation. Second off, we have our moment of area depending on the neutral axis, which is a times y, where a is the area and y is the distance from the neutral axis to the point being measured. Next, we have the shear flow, which is the shear force multiplied by the moment of area divided by the moment of inertia. Our shear stress is the shear force multiplied by the moment of area divided by the moment of inertia times the thickness. From here, we get to determine the force that's acting upon the beam, which is just the integral of the shear flow across the whole S section. So for our design considerations, we were thinking about the shear center, which we wanted to be where the sum of the moments were equal to zero. So we don't want any torsion about the center. And for this, we decided to collect voltages and find where the shear center was the same for both measurements. Our predictions for this mentioned that we will want our shear center of the C-beam to be on the outside and the shear center for the L-beam to be in the corner. This will be matching the axes of symmetry, which is expected.
Now we can see the experimental setup. On the left-hand side, we have a side view of our experimental setup, and on the right side, we have a top view of our experimental setup. So what we have in the center, you can see this in the side view. We have a silver section running down the middle, and that would be our specimen, our L channel or our C channel. On the top, right above that, we can see our linear potentiometers, and we have two linear potentiometers in order to do this experiment. And then on the right picture, on the top view, you can see that we had different places where we could put the weight, and these will all be discussed in later slides. And then we have pictures of our specimens tested. Like I said previously, we have a C channel and an L channel. The measurements of these beams are given to the right of the actual pictures in the same figures. And these are all important in the calculations of the shear center and are discussed later.
The first thing that we did for the experiment was calibrate the linear potentiometers. We did this while the potentiometers were detached from our main apparatus, and we did it by measuring the displacements of metal bars with known thickness. In our case, the bars were 1/8 of an inch thick. We used the voltages output by the potentiometers to calculate the calibration constant that we use in our data later to find the shear center. As you can see in the image on the right, voltage 1 was later mounted on the left, and voltage 2 was later mounted on the right. After this, we measured the dimensions of each column. They were the dimensions that we saw earlier on the previous slide. Moving on to our experiment, we needed to cause deflection on each of the columns, which require some sort of load. We decided to attach one 1-pound metal weight to a hanger that already weighed about 1.1 pounds. This brought the total attached mass to about 2.1 pounds. As we stated earlier, since the shear center has two axes at which there is no torsion, we needed to apply the load to two orientations for each column. So we collected voltages as the weight was shifted to different angles on the apparatus to find the shear center for both the C and L cross sections. And these are the theoretical shear center locations. For symmetrical beams, such as the L channel, the shear center should be at the intersection of the axes. And we calculated that the C channel shear center laid along the line of symmetry at 0.429 inches outside of the channel.
The calibration constants results from the slope of the thickness over the voltage. The calibration constant for the first linear potentiometer is about negative 0.61947 inches per volt, and the calibration constant for the second linear potentiometer is about negative 0.69688 inches per volt. The location of the load is the location with respect to the left side and is non-dimensional. The deflection was determined based on the voltage from the linear potentiometer multiplied by the calibration constants found previously. As seen in the figure, the deflection recorded for potentiometer 1 increases as the location of the load moves to the right. The deflection recorded by potentiometer 2 decreases as the load moves to the right. The shear center in this orientation occurs at about 0.47 along the x-axis, which is about 0.47 inches. Similarly to the previous figure, the deflection recorded by linear potentiometer 1 increases as the location of the load moves to the right, and the deflection recorded by the other potentiometer decreases as the load moves to the right. The shear center in this orientation is about 0.77 along the x-axis, which is about 0.77 inches. Based on the calculations from figures 6 and 7 and the orientation of the C channel, our measured shear center is close to the line of symmetry and outside the C channel. This matches our predictions for shear center of the C channel.
Like the C channel beam, the L channel beam was tested as well in two orientations. In orientation 1, the linear potentiometers gathered voltage data that was then multiplied by the calibration constant to get the deflection. The point at which the deflections are equal on the graph is the intersection point and corresponds to the percentage along the x-axis of where the shear center is in that orientation. In orientation 1, we can see that it's a little more than 40% along the x-axis. For orientation 2, the same thing was done. As the load moved across the x-axis, the deflection for linear potentiometer 2 decreased, while the deflection for linear potentiometer 1 increased. Again, the intersection point was found by finding the point at where the deflections are equal, and this ended up being almost 50% as expected along the x-axis. We then dimensionalized the percentage along the x-axis into our lengths, and we found that the shear center in orientation 1 was about 0.054 inches away from the corner. And then in orientation 2, we found that it was about 0.732 inches from the left side. In orientation 1, the shear center was found was almost as exactly as predicted at the corner of the L beam. However, orientation 2 varied a little bit. This may be caused by inconsistencies in the linear potentiometer or inconsistencies in the strength of the flanges of the beam.
So overall, the shear centers that we experimentally determined for both channels were relatively close. Our experimental shear center for the C channel beam was close in orientation 1 with percent error of about 5.8%, but it was further off in orientation 2, which is the one out on the the location on the outside with an error of about 17%. Our experimental shear center for the L channel though was close in both orientations with a 6.9% in orientation 1 and a percent error in orientation 1 and a 5.84% error in orientation 2. So again, very close. So for some of our errors and experimental difficulties, sources of error, we were having trouble with the linear potentiometers. They were giving us weird readings, and they had to be moving. We had to move around a lot to get it where it wasn't just like bottoming out. And difficulties during the experiment. Originally, we had three 1-pound weights on the hanger, but that kept crashing into the apparatus and was causing difficulties with the measurements. So we reduced it down to 1. But as a trade-off, having an increased rate would exaggerate the voltage readings and increase the clarity of the results, and probably would improve the precision. So it's sort of a trade-off. And then aligning the potentiometers to measure the voltages was troublesome. Again, we were having problems with them like zeroing out.